Hello and welcome to this video. In this video, I'm going to show you three things involving the vernier calipers. I've realized that most students have a problem reading the vernier scale, as well as determining the zero error, whether the zero error is negative or positive, and then how to get the actual measurement when you use a vernier calipers with a zero error. And I've realized that most students don't understand the concept of the zero error because, first of all, they do not understand the concept behind the vernier scale. The vernier scale allows us to measure readings up to a precision of 0.01 centimeters. The meter rule allows us to measure readings up to 0.1 of a centimeter. So in terms of precision, the vernier scale is more precise than the meter rule because it divides that 1 millimeter into 10 divisions and it can measure each one of these accurately. So this is the precision of a vernier scale. Well, this is the precision of a meter rule. So now how does that one work? Let's go back here to this tool that I've made. It is going to help you to be able to understand the idea of the least count. We are going to use this tool to try and practice getting various readings on the vernier scale, what we call the scale reading. And then we are going to determine the zero error, whether the zero error is positive or negative. And then we see if we're given a certain reading, can we be able to, a certain scale, can we be able to determine the zero error? So how does the vernier scale work? We're going to assume in this tool that from this point to this point is 1 centimeter. That is the length of this length here is 1 centimeter. Of course, we know the actual 1 centimeter on the meter rule is quite small. So, but I've expanded it like this so that this tool can just help you to understand what we are talking about here. So from here to here is 1 centimeter. Let me just remove this one first so that we can be able to concentrate on this scale here. So from here to here is 1 centimeter. I've divided this length into 10 equal divisions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what is the length of one division here? It's obvious that the length of one division will be 1 centimeter. We divide by 10 divisions. We are going to get the length of one division on the main scale. By the way, this one is referred to as the main scale. The other one is referred to as the vernier scale. So that one division from 0 up to the first division here, this one here, is obtained by dividing 1 centimeter by 10 divisions, and we find that that is 0.1 centimeter. So from here to here is 0.1. Therefore, from here to here is 0.2. From here to here is 0.3, 0.4, 0.5, 0.6, and so forth until we come here, we get 1 centimeter. So what is the length from here to here? Of course, it is 0.8. What is the length from here to here? It is 0.7. And what is the length from here to here? That will be 0.9. There is a reason why I want you to determine the length from here up to the 9th division on the main scale. Because when we bring in the vernier scale, we are going to see some striking similarities. So let me bring in the vernier scale here. And first of all, let me just cover up that one with this scale. we are going to see that on the Vernier scale, again, there is this division here, or there is this mark here, and there is this mark here. And then I have divided the distance between the two marks into 10 equal divisions. And I've numbered them 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We want to determine the length of one division on the Vernier scale. And that is why we want to compare the two scales together. So we are going to align the 0 mark on the Vernier scale, the 0 mark here, aligned to, on the main scale, aligned to the 0 mark on the Vernier. You will find that simultaneously, the 10th mark on the Vernier scale aligns itself with the 9th division on the main scale. That's why I wanted you to determine the distance from 0 all the way to the 9th division on the main scale, and you say that it is 0.9. Therefore, we can tell that the distance from here to here on the Vernier scale is also 0.9 centimeters, because the edges of the scales coincide. They are together. This coincides with this, and this one coincides with this. So it is clear that this length from here to here is 0.9 centimeters. So let me just cover that other scale so that it doesn't confuse you. Now that we know that from here to here is 0.9 centimeters, can you tell me how I can find the length of one division on the Vernier scale? How can I find this length? Of course, it is straightforward. It is just like what we did with the length of one division on the main scale. We took that length and then we divided by how many divisions we have. And you can see we've got 10 spaces here. So here we are going to divide 0.9 by 10. So, and let's do exactly that. So here we have the 0 mark on the Vernier, and then we have the next mark here, which we have called 1, and we want to determine this length here, and we have said it is 0.9 divided by 10, and we get 0.09 centimeters. It's obvious that when we compare the length of one division on the main scale and the length of one division on the Vernier, the length of one division on the Vernier is smaller than the length of one division on the main scale. As a matter of fact, when now I put them together, let me just dot this one like this, you can see that the length of one division on the Vernier is shorter than the length of one division on the main scale. What is the difference between them? This small division here, how can we get them if we know this is 0.1 centimeters and this is 0.09 centimeters? We can get this difference here, or this length here, just by subtraction. And we are going to say that length there is 0.1 centimeters. I get the longer one, which is this one here. I subtract the shorter one, which is 0.09 centimeters. I find the difference, and you can see that I'm going to get 0.01 centimeters. And as a matter of fact, if I compare the two, again, I return the Vernier in that position. I have to make sure that this 0, the 10th mark on the Vernier, coincides with the 9th division on the main scale here, while the 0 mark on the Vernier coincides with the 0 mark on the main scale, like that. When I compare the two lengths, it's obvious this one is longer than this one. And you can see that these two marks do not align together. It's because this one is shorter than that one. This short distance here, according to the model that I've made here, according to this tool, is 0.01 centimeters. So, and you can see that the difference between this one and this one here, this difference here is 0.01 times 2, because there are like 2 of them. This distance here is 0.01 times 3. There are 3 of them. This distance here is 0.01 times 4, 0.01 times 5, 0.01 times 6, 0.01 times 7, 0.01 times 8, 0.01 times 9, and of course here they coincide. There is a reason why I have gone that way, because when we'll be talking about the zero error, we'll be trying to see how far a certain division moves either to the left or to the right. Let's go back to our blackboard here. This length here, the difference between the length of one division on the main scale and one division on the vernier is referred to as the least count. Least count. For example, let me just remove this one just to explain to you what the least count means. This again is a scale that we find on a meter rule. It is graduated in terms of centimeters and 0.1 over centimeter. So from here to here is 1 centimeter, 2 centimeters, 3 centimeters, and so forth. But because this 1 centimeter has been further divided into 10 other divisions, we can count in steps of 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1, 1.1, 1.2, and so forth. You can see that I am increasing, to get the new value, I'm increasing the previous value by 0.1. In other words, I am counting in steps of 0.1. So we can say the least count on a meter rule scale is 0.1. Understand the idea of the least count. We are literally counting, but what is that smallest division that we are counting? What is the value of that small magnitude? It is referred to as the least count. So the least count on a meter rule scale is 0.1 centimeters. On the vernier scale, you have seen that when we combine out these two scales like this, we can count in steps of 0.1. For example, when I move now the vernier through a short distance to the right, I start at this point where the 0 here coincides with that 0. This 10th mark coincides with this 9th division. If I just move this vernier scale to the right, just slightly, which divisions do you think are going to coincide? Let's do that and see what happens. So I'm moving it, I'm moving it, I'm moving it. And you can see the next division which coincides will be this one. It coincides with that one there. What does that mean? Let's take it back to where it was. Remember, we have already determined that this distance here is 0.01 centimeters. So when I move the vernier scale to the right so that the two marks now coincide like that, it means that this mark has moved to the right through a distance equal to 1 least count. Understand that. If I continue moving it to the right, let's see how far this one moves. What division do you think is the next one to coincide? Of course, it will be this one here. Let's do exactly that. And I move it to the right. And once the two divisions coincide, then this 0 mark on the vernier scale has moved to the right through a distance equal to 2 least counts. And I can continue like that. Again, move it to the right through a distance equal to 1 least count, like that. And will be able to agree with me that this distance is equal to 3 least counts. I continue like that. I move it until the 4th division is coinciding with the division here. then it means this is 0.04 centimeters. I can continue like that until I have the fifth one, which is moving, and I can see that this distance here will be 0.05. You can see that I'm able to count in steps of 0.01 centimeters. That is why this is referred to as the least count, the smallest division at which I am counting. So I'm moving from 0.01, 0.02, 0.03. You can see that I am adding 0.01 to the previous value in order to get the new value. So I can continue like that until now it is the sixth division which is going to coincide like that. Next, it is the seventh division which will coincide. Next, the eighth division which will coincide. Next, the ninth division which will coincide. And then at this point, when I move it like this, we go back to the starting point where the 0 mark on the vernier coincides with this mark on the main scale, while the 10th division or the 10th mark on the vernier scale coincides with the 1 centimeter value. So through how much distance has the 0 mark on the vernier moved to the right? It has moved to the right through a distance equal to 0.1 centimeters. But before we get to 0.1 centimeters, we were able to count in steps of 0.1, 0.1, 0.1, 0. We were able to count in steps of 0.01, 0.02, 0.03, 0.04. And I'd like you to observe that the coinciding division tells us how many least counts we have covered so far. Remember, we have not marked this. It is impossible to mark 1 millimeter on any one scale. It's impossible to see when we mark those divisions on the scale. Now, this scale helps us to mark those divisions on this particular very small space, which is 1 millimeter. Understand that the aim of the vernier scale is to subdivide one division here into 10 equal divisions, and we would be able to know how many divisions we have covered this way without actually marking them on the scale. That is the aim of the vernier scale. So I hope this helps you. It appears to be quite detailed, but you will be able to understand this. It becomes much easier now to understand anything to do with this vernier scale if you understand the theory behind it. So that is how the value of the least count of the vernier scale is obtained. All you need to do is get the length of one division on the main scale, the length of one division on the vernier scale, find the difference, you will get it to be 0.01 centimeters. And I have an exercise for you, and it will be a good exercise if you try it out. Construct one whereby now you subdivide this space here into 20 divisions or into 5 divisions. You can use values such as 5, 20, 50, and so forth, and see what kind of scale you come up with. So that exercise, you can do it much later. So we have seen that if I move this one to the right like that, it allows me to get the length from here to here, which is 0.01 centimeters. If I move in such a way that the second one is the one coinciding, this is 0.02 centimeters. If I move it such that it is the third one which is coinciding, this length here is 0.01 centimeters. Supposing I were to move it in such a way that now this is the case. What is the length that has been moved by the 0 mark on the vernier scale? What is this length? So first of all, we'll be able to observe that after every 0.1 centimeters, this vernier scale repeats itself. So in order to find out how many times it has repeated itself, we'll have to know that this one is 0.1 centimeters. Then it repeats itself. This is another 0.1. So this one is 0.2. We want to know how many divisions is from here to here? How many least counts is from here to here? How do we know how far we have moved from here to here so that we can add it onto this one? How do we know that? It's very simple. We just check on the Vernier scale and find a division here which coincides with a division here. And you can see that the only division which coincides is the fourth division. So the first thing we do is that we write down this value here, 0.1, 0.2. So we are going to write 0.20 centimeters. Then we check the coinciding division, and we've seen that the coinciding division is the fourth one here. So we are going to get 4. In order to get how many least counts there are here, we multiply 4 by that value, and this one is going to give us 0.20 plus 0.04, and we get 0.24 centimeters. It's just as simple as that. Let's try another one. I'm going to just put it at random, at any value there, maybe something like that. What is the reading here? In other words, we are now reading the scale. We are reading the scale. How far has this 0 mark moved? It has moved from here all the way to here. And how many divisions are those on the main scale? 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. So I'm going to write 0.8. 0. I add. Let's check the division here which coincides with the division here. And it is the second one. If I multiply 2 by the value of the least count, I get 0.02. And that becomes 0.82 centimeters. Let's check another reading. Can go up to some point there at random there, and I can see that, let me make it exact, it is the 8th division which is coinciding. And how far has it moved? 1, 1.1, 1.2, 1.2. I again write 1.20. I check the coinciding division. It is the 8th one. I multiply by the value of the least count. I find that it gives me 0.08, and that is 0.28 centimeters. You can see how easy it becomes. So this tool can help you to be able to understand or to be able to get any reading. I've just constructed this tool in order to help some of you who have got a problem in reading the scale. First of all, it helps you to understand how we get the value of the least count, and then it helps you to understand what it means by scale reading. We have seen how we do the scale reading, and then now I want to show you how you determine the zero error of a Vernier scale. Because when you're using analog measuring instruments, it's important that you determine its zero error. So we want to see how you determine the zero error of a Vernier scale. How do we do that? Zero errors can either be positive or negative. We are going to start with a scale which does not have any zero error. In order to determine the zero error of a measuring instrument, what we need to do is to close the jaws of the vernier calipers. Here I have excluded the jaws of the vernier calipers because I'm just interested with the scale. But in order to determine the zero error, you close the jaws without any object in between them. So, and then you look at the scale. If you close the jaws without any object in between them, and you find that this 0 coincides with this 0, and simultaneously the 10th mark on the vernier coincides with the 0.9 centimeter mark on the main scale, then this vernier calipers does not have a zero error. Understand that. So we start from a point where the vernier calipers does not have a zero error. And then now we go to a situation whereby the error is positive. If you find that for some reason they don't coincide, these two don't coincide, and that the zero mark on the vernier is to the right of the zero mark on the main scale, then this vernier calipers has a positive zero error. Understand that. How do we get that positive zero error? So let's move back to a situation whereby it does not have any error at all. And then we move it to the right just slightly. You'll find that the next division which coincides will be the first division and this one. That means that this one is a positive zero error of this magnitude here. So how much is it? It will be positive 0.01 centimeters. Now, what does it mean when we say that the zero error is positive 0.01? It means that if you are to use that vernier calipers to measure any length, you will find that if you get the scale reading, if you get a scale reading of maybe 5.73 centimeters, you are trying to measure the length, a given length, and you get a scale reading of this much, and the vernier calipers you are using has a zero error of 0.01 centimeters. What this means is that the actual length that you are measuring will be less than what you are reading here by this value. In other words, you're going to get the scale reading, which is 5.73. You subtract the zero error, 0.01, and you get 5.72 centimeters. That is what the zero error means. It means that whatever you read on the scale is not the actual length that you are measuring. In this case, if the zero error is positive, it means that the scale reading is greater than the actual length by a value which we call the zero error. So in order to get the actual length, what you do is you get the scale reading, you subtract the zero error. Let's get a different, maybe a zero error, something like that. Can you be able to determine the zero error here? Of course, you can be able to see that the zero error is this much here, and it is given by the coinciding division here, which means the zero error is positive 0.03. And again, if you are to use that vernier calipers to measure any length, it means that the scale reading will be greater than the actual length by a value equal to 0.03 centimeters. So in order to get the actual length, you will again use this equation. You'll get the scale reading, which I've shown you how to read. You subtract the zero error. So I hope that one helps you to understand the zero error, the positive zero error. Now let's go back to a situation whereby the vernier calipers does not have any error, and that is the way it looks like. Suppose when you come here and you find that the zero mark on the vernier is to the left of the zero mark on the main scale. Again, it means that there is a zero error. There is a zero error in that measuring instrument, in that vernier calipers. But how much is it? This one is usually a little bit tricky. It's not as direct as the positive zero error. So pay close attention to how I will go about it, because it will make your life much easier when you're reading when you're using the vernier calipers. Again, let's go back to a situation whereby it does not have any error at all. Remember, you have closed the jaws, and when you look at the scale, this is what you see. So Suppose now we want to move the vernier to the left through a very tiny distance equal to 1 least count. Which division do you think will be the next one to coincide? Remember, if I moved it to the right, this one was the one. If I moved this vernier scale to the right, this was the division which would coincide with the division here next, because this distance is very small and the lower part is the one which is moving. Okay, but here I'm now moving it to the left. You see, this one will not be the next one to coincide. In any case, that distance is going to increase. This one will be increasing further. So I'd rather look for a situation whereby I'm looking at this one and this one. And that is when I go all the way to the left here. And when I start with a scale, again, I go back to here, to this point, whereby there is no zero error. If I move this vernier scale to the left through a distance equal to 1 least count, you will agree with me, it is the 9th division on the vernier scale that will coincide with this division here. And let's do exactly that. So I've moved the vernier scale to the right, just slightly to the right through a distance equal to 1 least count. So you can see this one has moved to the left through a distance equal to 1 least count. The 10th mark also has moved it to the left through a distance equal to 1 least count. So here the error is negative 0.01 centimeters. 0.01 centimeters. That will be the error. Now many times, and this is where now many people make a mistake. They think that getting the positive 0 error on the vernier scale, the way they do it, is the same way they do it when getting the negative 0 error. Of course, we follow the same steps, but this time, when it comes to looking at the next division which will coincide, although it is the 9th division, that does not mean that the negative error is negative 0.09. That will not make sense, because an error of negative 0.09 is so big. It's close to this one here. It's close to almost this one here. Okay? But when you look at this difference here, it's obvious. It's common sense. This cannot be equal to negative 0.01. I mean, it cannot be equal to negative 0.09, although it is the 9th division which coincides. I'd rather look at it from this other end and see that from here, if I were to move to the left until this is the division which coincides, then it has moved to the left through a distance equal to 1 least count, and I can see it from here, and that is why I write it here like this. Okay, if I continue moving it to the left through another least count, now it has moved it to the left through 2 least counts, and it is now the 8th division which is coinciding. How about to the left through a distance equal to 3 least counts, it is the 7th division which is going to coincide, and this distance here is 0.03. It's negative because the 0 mark on the vernier has moved it to the left. So let me give you an easier way of determining the 0 error if it is negative. Again, we move here where there is no 0 error. What we are going to do is that we are going to reverse the naming of these divisions. Instead of moving to the right like this, you know, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I will name them with this one being 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 10th mark on the vernier scale becomes 0. The 9th mark becomes 1. The 8th mark becomes 2, and so forth. So just imagine that you've got 0, 1, 2, 3, 4, 5. Now let's move this vernier scale to the left through a distance equal to 1 least count, and it is here. It is this one here. So this one will be 0, 1. And you can see, since it is this division here which is we have called 1 coinciding, then the error is negative 0.01. Again, we continue moving it until it is the 8th division which coincides with this division here, the error will be negative 0.012, 0.02, negative 0.02. We continue. That will be negative 0.03. How am I getting this? Well, this one is negative 0.04. It's because, although it is a sixth division which is coinciding, I am counting from the left. 0, 1, 2, 3, 4. Fourth division coinciding. Error is negative 0.04. I hope this one helps you to understand that concept. Now let's see what it means when we have a negative 0 error. Let's say maybe when we use what will be the scale reading. Assume this length here is the same one which we are measuring. This one 5.72. How much do you think will be the scale reading if we are using a vernier calipers with a negative 0 error? Of course, when we are using a vernier calipers with no error, it will give us 5.72 directly. But if we are using one with the positive 0 error, the scale reading becomes 5.73. If we use a vernier calipers with a negative 0 error, the actual length, which is 5.72, will be equal to the scale reading, which we don't know, we call it x, minus 0.01. Remember, the error is negative 0.01. We are measuring a length whose actual magnitude is 5.72, is the same as this one. We want to find out how much will be the scale reading. So this one will be equal to x minus gives me positive 0.01. Of course, this is 5.72. And if we manipulate this, we are going to find that x is going to be equal to 5.72 minus 0.01, and we get 5.71 centimeters. Now you can see that the scale reading will be less than the actual length that we are measuring when we use a vernier calipers with a negative 0 error. But the same equation is used. Actual length is equal to scale reading minus the 0 error. What I want you to observe is what has occurred here. When you're using the negative 0 error, there is minus, but the error has got a negative sign of its own. Here, the error had a positive sign. Negative and positive, they give you negative, but negative and negative, they give you positive. That is what I want you to observe, because you just need to recall one equation. Actual length is equal to scale reading minus 0 error. There is no need to formulate two equations. Just use one. Remember what happens when the error is negative. That is what I want you to be careful about. So let me give you another error, and at random that would be the error. How much is the error? First of all, that error is negative because the 0 mark on the vernier is to the left of the 0 mark on the main scale. Negative. What is the coinciding division? A 0, 1, 2, 3, 4, 5, 6. So negative 0.06. So that is how you would read the scale of a vernier calipers. First of all, you understand what is meant by the least count. Next, you practice reading the scale of the vernier calipers. Next, you look at the 0 error. First of all, you start with a situation whereby the error is, there is no error. You go to positive error. You practice how to read that. You go to negative error. You practice how to read that. And then now you ask yourself, supposing I'm using a vernier calipers with an error, whether positive or negative, how can I be able to determine that error? How can I be able to determine that error? And how can I be able to determine the actual length that I am measuring? Those are some of the questions that you need to ask yourself when you are using this instrument. So I've made this tool. If you're a teacher out there and you would like to get this tool in order to assist your student to be able to do 3 things: understand the least count, which will make them to understand how to read the Vernier scale, determine the zero error, whether it is positive or negative, and have them practice how to read or how to read the various negative errors, whether it is positive or negative. I'm putting out this tool out there, and for a small donation to this particular channel, I can allow you have this particular tool. It's quite cheap. It's not expensive. Like you can see, I've just made it just here at home, and I think it's going to change the lives of your students if you just acquire it for a small donation to this particular channel. The other thing I'd like you to do as a member of this channel, maybe it is the first time you are seeing my videos, I'd like you to go right ahead and subscribe, because this one helps the channel. When you watch a video like this one, you find that it's good, that is going to help other students out there. I'll appreciate if you share this particular video with your colleagues. As a teacher, send it to other teachers who can be able to use it with their students. If you're a student and you're watching this, I'd also like you to share this video with your friends, and maybe even ask your teacher to get this tool so that you can practice with it. So long as I have your address, I'll be able to mail this particular tool directly to you. I've made 10 sets. 10 sets are remaining, so be the first one to get this particular tool. And remember to give this video a thumbs up, and I wish you all the best as I teach you another skill in another lesson. Goodbye.